Hello friends, welcome back to my channel Path of Physics. In this video, we are going to discuss about Stefan's law and an experiment to determine Stefan-Boltzmann constant. So, Stefan's law or Stefan-Boltzmann's law was formulated by Russian physicist Joseph Stefan. Later, his former student Ludwig Boltzmann deduced the law from thermodynamical considerations, so the law is also called Stefan-Boltzmann's law. The law states that the total amount of radiant energy emitted per second per unit area of the surface of a perfectly black body is directly proportional to fourth power of its absolute temperature. The total amount of radiant energy emitted per second per unit area of the surface of the perfectly black body is the emissive power E of the black body. Now the law states that the emissive power E of the black body is directly proportional to fourth power of absolute temperature. E is proportional to T raised to 4. Now, removing this proportionality symbol, we get a constant E is the equation E is equal to sigma into T raised to 4. This sigma is Stefan-Boltzmann constant. Its value is 5.67 into 10 to the power minus 8 watt per meter square Kelvin raised to minus 4. Now, E is the emissive power and T is the temperature. Now consider a black body. If the black body is at temperature T1 and it is surrounded by another body at temperature T2, then it will emit radiant energy at the rate of sigma T1 raised to 4, and it will also gain energy at the rate of sigma T2 raised to 4 per unit area from the surrounding body. So the net emissive power of the black body is E is equal to sigma into T1 raised to 4 minus T2 raised to 4. Amount of energy radiated in T seconds is given by Q. Q is equal to, from this equation, we derive Q from this equation, E is equal to Q by AT. So Q is equal to E times AT. We know what is the value of E from our previous equation. So Q is equal to sigma into T1 raised to 4 minus T2 raised to 4 times AT. Now, if the body is not a black body, then the emissive power E is equal to emissivity. This is emissivity. It is denoted by small e. I have discussed about this in my previous video. So, emissive power capital E is equal to emissivity small e times sigma into T1 raised to 4 minus T2 raised to 4. Amount of energy radiated in T seconds is given by Q is equal to emissivity small e times sigma into T1 raised to 4 minus T2 raised to 4 into AT. Now remember two things. Stefan's law is law of emission. It does not refer to net loss of heat by radiation due to exchange with its surroundings. It is law of total emission, that is, the emission is not confined to any particular wavelength or any narrow group of them. So this is all about Stefan's law. Next, we have an experiment to find Stefan's constant. So this is the experimental setup. The apparatus consists of a hollow hemispherical metallic vessel A. Its inner surface is coated with lamp black. Then this metallic vessel is kept inside a wooden box. The wooden box has a steam inlet and steam outlet. It has two thermometers inserted in it to measure the temperature of this hemispherical vessel. The bottom of this hemispherical vessel is covered with wood, and the center bottom of this hemispherical vessel contains a hole to insert a silver disc. And the silver disc is covered with this covered and uncovered by this ebonite cover by adjusting this handle edge. Now this upper surface of the silver disc is coated with lamp black. Now, a thermocouple is used to measure temperature difference. What is thermocouple? It is a sensor used to measure temperature difference from measuring potential difference. Okay. Thermocouple is a device. It consists of two different metals, the metals are welded in such a way that two junctions are formed. One junction will be at one temperature and the other junction will be at other temperature. So due to this temperature difference, there will be a potential difference developed. This potential difference can be measured, and from this potential difference we can calculate the temperature difference. So this is how thermocouple's principle works. Now, this is a thermocouple. Its one junction is immersed in this test tube containing oil. This test tube is placed in a water bath. This setup is provided so that there is no sudden temperature change, and the other junction is soldered to this silver disc B. Then a galvanometer is connected across the junctions of this thermocouple to measure the potential difference, and the leads to the galvanometer are immersed in a beaker containing cotton wool, in a bath containing cotton wool. So this is the experimental arrangement. So I will read the apparatus once more. It consists of a hollow hemispherical metallic vessel enclosed in a wooden box. The inner surface A is uniformly coated with lamp black and the wooden box is lined with tin plates. There is steam inlet and steam outlet. There are two thermometers inserted in the wooden box T and T to measure temperature of A. So these thermometers are T and T. There is a hole at the bottom center of the hemispherical vessel to insert a silver disc B, whose upper surface is coated with lamp black. Why we are coating with lamp black? Because lamp black can act like a black body radiator. So that's why we are coating the inner surface of the hemispherical vessel, hollow hemispherical vessel, with lamp black, and this upper surface of the silver disc with lamp black. Okay. Now the hole is initially closed with ebonite cover. Handle H is used to adjust the ebonite cover. A thermocouple is used to measure temperature difference. It is a type of sensor. It measures temperature from the potential difference across its hot end and cold end. I told you one junction of the thermocouple will be at one temperature and the other junction will be at other temperature. So there will be a hot end and cold end. It consists of two wires of different metals. The two metals are connected through welding in such a way that two junctions are formed. One of the junctions of thermocouple is immersed in a tube containing oil and the other junction is fixed to the bottom face of the disc. The tube is surrounded by a beaker containing water. This setup is used to reduce sudden temperature change. Then a galvanometer is connected across the junctions to measure potential difference. The leads connected to the terminals of the galvanometer are immersed in cotton wool. Now this is the experimental apparatus. Now we can move on to our experiment. Our experiment consists of two steps. Initially, B and E are at room temperature. So the junction immersed in oil is heated, so there is a temperature difference between B and E. Galvanometer shows deflection. For various temperatures of hot junction, galvanometer deflection is noted. So that is initially this region is E. This junction of the thermocouple and this junction of thermocouple. Consider these two junctions. And initially this both the junctions are kept at room temperature. Then this water bath is heated so that this junction becomes a hot junction or the hot end and this becomes the cold end. This is the disc is kept at room temperature. So there is a temperature difference. For this, due to this temperature difference, a potential difference is developed, and due to this potential difference, galvanometer shows some deflection. For each temperature difference, galvanometer for the temperature for different temperature difference, galvanometer deflections are noted. For various temperatures of hot junction, galvanometer deflections are noted. Then a graph is drawn by taking difference between the temperature of hot junction and room temperature. That means the cold junction along the y-axis and the galvanometer deflection along x-axis. So this is how we get the graph. Now we have to calculate the slope of this graph. Slope of this graph is tan alpha. It is equal to AB by BC. Now this is equal to dt. dt is a temperature difference, and dt by d theta. Theta is the galvanometer deflection. So tan alpha is equal to dt by d theta. This is the slope of our graph. Now next step is measurement of dt by d capital T by d small t. D capital T is the temperature difference and d small t is the time interval. So for that, both the junctions of the thermocouple are allowed to reach room temperature. Then steam is passed. The disc is covered by the ebonite cover. The hemispherical vessel becomes heated. After some time, the thermometers T and T shows a steady temperature. This means hemispherical vessel has reached steady state or uniform temperature. Due to this heating, temperature of lamp black inside the vessel increases and it acts as a black body and emits radiations. The radiations are prevented from escaping into the surroundings by ebonite cover. After the hemispherical vessel reaches steady state, the silver disc is uncovered by adjusting handle H of the ebonite cover. Radiations will fall on the disc B. Disc B's temperature rises. The junction of thermocouple attached to B becomes hot, and as its temperature rises, there will be temperature difference between the two junctions, which causes deflection in galvanometer. The deflections in the galvanometer are noted after equal intervals of time, say 10 seconds. So once more I will explain. So after the standardization of thermocouple, these two junctions are allowed to reach room temperature. After that, steam is passed. So this hemispherical metallic vessel gets heated. The lamp black inside it gets heated. After some time, this hemispherical metallic vessel reaches steady state condition. Both the temperature readings of both the thermometers will remain constant or and same with time. And the lamp black, it now acts as a black body radiator. It emits radiations. After reaching the steady state, this ebonite cover is slightly tilted, so these radiations will fall onto the silver disc B, upper surface of the silver disc B. Now this silver disc B, upper surface of the silver disc B will absorb these radiations. Now, so this junction, the thermocouple junction attached here will act as hot junction, and this junction will remain in room temperature. So this junction is cold junction and this is the hot junction. In our standardization of thermocouple, this was the hot junction and this was a cold junction. Now it is reversed. This is the hot junction and this is the cold junction. So there is temperature difference. Due to this temperature difference, potential difference is developed, and due to this potential difference, galvanometer shows some deflection. So the galvanometer deflection is noted after every 10 seconds, okay, and a graph is plotted. So we get a graph like this, and take a point D, draw tangent through this point D and calculate its slope. Its slope is EF by GF. It is tan beta. Slope is equal to EF by GF. It is equal to tan beta. It is equal to dt by d theta. Okay, dt, d small t by d theta. we plot the graph by taking time in y-axis and deflection theta in x-axis. Okay, time is taken in seconds. Now this is the experimental part. Now let's go to the theory part. When the steam was passed, the hemispherical disk got heated. The lamp black also got heated due to temperature rise. Now it emits radiations. Later these radiations are received by disk B. Amount of heat emitted per unit area in unit time by hemispherical metallic vessel is R1. R1 is equal to sigma into T1 raised to 4. So R1 is the emissive power of the hemispherical metallic disc. Now this heat is actually absorbed by B. So amount of heat absorbed by B per unit area and unit time is also R1. It is equal to sigma into T1 raised to 4. Now due to absorption of radiation, B's temperature rises and it starts to emit radiations. At T2, due to absorption of radiation, B's temperature rises and it starts to emit radiations. At T2, B emits radiations. Let's say at temperature T2, B emits radiations. You know that B's upper surface is coated with lamp black. So it also acts as a black body radiator. So the amount of heat emitted per unit area in unit time by B is R2. R2 is equal to sigma into T2 raised to 4. Now remember that not all absorbed radiations, remember that not all absorbed radiations is emitted by B. Part of it is used to rise temperature of B. Net heat absorbed by B per unit area per unit time is R1 minus R2. Now this heat is used to rise temperature of unit area of B. So R1 minus R2 is equal to sigma into T1 raised to 4 minus T2 raised to 4. Net heat absorbed by B in unit time is R1 minus R2 times A, where A is the upper surface area of the disk. This much heat is used to rise temperature of B in unit time. So this R1 minus R2 times A can be written as ms dt by d capital T by d small t. So this is our equation number 7. Now substituting the value of R1 minus R2 times R1 minus R2, we get from this equation we are substituting the value of R1 minus R2. This is R1 minus R2 is sigma into T1 raised to 4 minus T2 raised to 4. So substituting this value we get sigma into T1 raised to 4 minus T2 raised to 4 times A is equal to ms dt by dt. Now this can be written as sigma is equal to ms by A into T1 raised to 4 minus T2 raised to 4 times dt by d capital T by d small t. T1 is the what is T1? T1 is the steady state temperature of the hemispherical metallic vessel or the enclosure. T2 is the temperature of the disc. How to calculate T2? The deflection in the galvanometer corresponding to point D is chosen for drawing the tangent on the graph is noted. For this deflection, temperature difference from the first graph is noted and room temperature is added to this temperature difference. This is how value of T2 is calculated. Once more I will explain. We selected this point, right, D, and the deflection corresponding to this point is found out, and this deflection from the first graph we find out the temperature difference. For this deflection we find out the temperature difference. To this temperature difference we add the room temperature value, so we get the value of T2. Now to find, next we have to find dt. This in this equation we know the value of ms. M is the mass of the silver disk. S is the specific heat capacity of the disk. A is the upper surface area of the disk. We know T1. I explained how to calculate T2. Now next we have to find d capital T by d small t. So to find d capital T by d small t, we have tan alpha is equal to d capital T by d theta, and tan beta is equal to d small t by d theta. Okay, from the first two equations. So d capital T by d small t can be written as d capital T by d theta times d theta by d small t. Okay. Now this we know what is d capital T by d theta. This is tan alpha. Now d theta by dt is 1 by tan beta. Tan beta is equal to d theta by dt by d theta. So d theta by dt is equal to 1 by tan beta. So this is tan alpha by tan beta. So on substituting this value to this equation, sigma is equal to ms by a into t1 raised to 4 minus t2 raised to 4 times dt by dt. We get sigma equals ms by a into t1 raised to 4 minus t2 raised to 4 times tan alpha by tan beta. So this is our required equation, our equation to find Stefan Boltzmann's constant. So that's all for today. If you have any doubts, please comment on it. Thank you.